Okay, so this is section 4.3, question 2. This is the second video. I'm going to do it also using the prime notations. So let's go back to the question here, and we're going to say, okay, look, guys, you can kind of see that this is x, all right? It gets smaller, and the angle changes as well. And so we can say that x, that this distance changes with time, okay? And so this side is x as a function of time. And this angle is also a function of time. And so you can kind of write like f of x, but really we're just going to use different variables that make sense with what we're talking about. X of t, okay, and theta of t. If using x is a you don't like it, then you can use a d. The problem with using a d is that you end up getting dt up here, and you get two d's, which I guess isn't a big issue, but you end up with a lot of d's if you use d's. So that's why I think a lot of people end up using x for distance. Okay. Anyway, note that x changes with time and theta also changes with time, and they change at a specific rate that may or may not be changing itself, right? So at every moment in time, they have a rate at which they change. Those can be written down as x prime of t, or the rate of change of x with respect to t. Well, this is given as -1. Remember over here, they said that the guy walks closer to this thing by 1. And they want to know the rate of change or prime of the theta of t, okay? And then they tell you to focus in on the variable x when it's exactly 10. Okay, well, this green stuff comes from this triangle over here. This is the moment when it's 10. We know that when x is 10, theta is this value, okay? But let's back up for a moment and let's actually look at the equation as a whole when x is still a variable but not fixed at 10. You don't want to put a 10 right here because then this will differentiate to equal 0. Anyway, so now if I take the derivative of this, now you can really clearly see that you have a chain rule, I think. So you take the derivative of tangent, you get secant squared, and you replace whatever was written there, okay? And then theta, um, the derivative of theta gets written here, okay? And then the same thing, you're going to differentiate this side with respect to t, not with respect to x, remember? So you're differentiating with respect to time, and you end up getting a negative 23 over x squared, because it's the derivative of 23 over x, is a negative 23 over x squared. And then you have to rewrite this function in there, and then you take its derivative and write it here. Fortunately, we actually know its derivative. It's always -1, all right? So I can place the -1 there. All these numbers are just nice and easy, but then x is 10. So this x of t is 10, because basically this is like, hey, what's x at the time that you're interested in? Well, we don't even really know the time, but we do know that we're interested in when x is 10, okay? And so I can go ahead and place that as a 10, and then theta, I can write that as well. And then there I end up getting my answer like that, because right here, theta prime of t, that's actually, again, what we were looking for, and it moves over, all right? Notice these t's just end up going away. Like, you're just like, whoa, what happened to the t, man? Like, it's gone. We don't even know the time it is. No, as a matter of fact, we never find out. I mean, we could find it out if we want, but we don't need to. We never find out the actual time it is that the guy is at this location, right? We just know that it's when x is equal to 10, all right? Now, I said we could figure it out, but we'd have to set a specific starting point at that point and say, like, you know, let's say he was back here at 20. Anyway, don't worry. The point is you don't have to worry about the time. You're actually differentiating with respect to time on this thing, and the time variable ends up never even showing up in terms of like an actual. I mean, it's there, but anyway, I'm babbling now, but you understand hopefully what I'm trying to say there. Okay. By the way, I also wanted to say, remember, both theta and x change with time, meaning theta can be written as theta of t, x can be x of t, and remember the derivative of theta would be dt or or prime, theta prime, or dx dt is equal to x prime.